this thing on? Is it running? It must be running. Let's go. Hey, you guys, welcome. This is activity 3 from the math book. This is page 165 if you're following along in your books. I hope you have some highlighters, some things to write with, maybe some multicolored pens. Do math in color. We're talking about an idea that's been around in geometry for thousands of years, going all the way back to the Greeks. And it's this idea of a postulate and a theorem. A postulate, so let's highlight. Ooh, first of all, by the way, sorry. I started to highlight over here the habits of mind. Do the same as well. Highlight reason abstractly, quantitatively. Highlight construct viable arguments and critique the reasoning of others, because that's what we need to do today. A theorem, a postulate, there we go. A postulate is a statement that is taken to be true without proof. Now, there's some argue on this one, but an example of that could be that 1 + 1 is 2. Do you have to prove that 1 + 1 is 2? No. I mean, maybe at some point you did, but it's now a statement that doesn't require proof. This is a postulate. A theorem is a statement that can be demonstrated to be true by using accepted mathematical operations and arguments. Maybe you didn't realize it, but 3 squared really means 3 times 3, and 3 times 3 is 9. So for us, as a theorem, if you didn't know what squared meant, you might need to be reminded that squared, like the little 2, means you got to take the 3 and multiply it by itself twice. 3 times 3. That's a theorem because you have to prove it with concepts. Here's another theorem that you need to know. A squared plus b squared equals c squared. That's literally the Pythagorean theorem. Theorem because it's a statement that can be demonstrated true by accepted mathematical operations and arguments. Okay, Euclid. There's a street in the neighboring town. I'll let you figure out which one it is. But they have this street there called Euclid. And I wonder if it's named after the Greek mathematician, also known as the father of geometry. Boom. This is an artist rendition of Euclid. He was a librarian at the famous Library of Alexandria. The Elements is a book written by the Greek mathematician Euclid. He used a small number of undefined terms and postulates to prove, there's that Greek math word for us, prove many theorems systematically. As a result, Euclid was able to develop a complete system we now know as Euclidean geometry, which really just means these 5 statements. The first one, a straight line segment can be drawn joining any 2 points. There are 2 points. We can draw a straight line segment between those 2 points. That's the first postulate. Postulate 1, I made it. Okay. Postulate 2, any straight line segment can be extended indefinitely into a straight line. So if you have a segment, put arrows on the ends of it, and you will have a line. So this is postulate 2. All right, there we go. Postulate 2. Take your line segment and extend it. That's checkbox 1, checkbox 2. All right. Given a straight line segment, reading postulate 3, a circle can be drawn. Kind of a weird way of saying it, but it's saying that you can draw a circle because you have a segment. So here we go. I'm going to draw a circle. The length of my circle is exactly going from point to point. It's going from the center on one point to the other, and then maybe use a different pen here. Here we go. Ooh, come on, no work. I have these amazing, these are like the best compasses ever. Oh my God. This is garbage. We can draw a circle using a line segment and calling that line segment the center. So disappointed in that circle. All right angles are congruent. Now, the easiest way to talk about right angles is to have Post-its. Uh-oh, where are my Post-its at? Well, I'll say that the corners of a piece of paper are what allow us to produce the... Oh, here we go. I got some cards. Yeah, repping the Carnegie Learning. Let's go. Okay. So you have right-angled corners on the edges of a card. And if you put them together, that right angle and that right angle, both of those together are the same. Choose different right angles. So here's a right angle and here's a right angle, and both of those are the same. Choose a different right angle and this right angle and this right angle. Those are both the same. So in other words, all right angles are congruent. Yeah, because they are 90 degrees. So all 90-degree numbers are the same. All right. This last one, postulate 5, blew people's minds. Like, it wasn't until within the last 150 years that they actually understand postulate 5 in different ways. And the way that they understand it now, oh my goodness, it is 100% a game changer. If two lines are drawn that intersect a third line so that the sum of the interior angles on one side is less than two right angles, and the two lines inevitably must intersect each other on that side if extended far enough. Wow. Okay, here's what he meant. He meant take one parallel line, so one line, draw the line parallel to it, and then, so there they are, here's line, and another line. And then if you draw a line that crosses both of those, so something that goes like so, when you do that, the sides, these angles right here, angle 1 and angle 2, those angles are exactly the same as two right angles, meaning angle 1 and the measure of angle 2 together, they will add up to 180 degrees. Almost as if like a straight vertical line was drawn through them and made two right angles. 90 plus 90 is 180. These are not 90s, but they're close. It turns out like only like 100 years or so ago, they realized that's not. What would it mean if they didn't have 180 degrees? What if there were more? What if there were less? And then we have like the geometry of things flying around in space. Okay. Finishing out this section, getting ready for next videos, we're going to do some stuff. Euclid used only the first 4 postulates to prove the first 28 propositions, or here's the vocab word, theorems. We have postulates and theorems. He was able to do a lot of math with the first 4. He didn't need the 5th postulate, this parallel lines one, until the 29th theorem. Can you imagine coming up with a list of 28 things where you've used only 4 ingredients? Imagine like making a recipe and then you've spent time preparing 28 complete meals, dishes, food items, and then using only 4 ingredients, and then you bring in a 5th ingredient only after you've made 28 of them. That was his way of doing things, but with math, where he was able to make 28 things, 28 statements, without talking about parallel lines. The elements also include 5 common notions. These are like, duh. So first of all, things that equal the same thing are also equal to each other. Let's bring in some algebra for this conversation. Let's say x equals 2 and y equals 2. I mean, I don't know what x and y are supposed to be, but they're just variables. And if they both equal 2, then x and y must be also equal. If equals are added to equals, then the wholes are equal. That's the next notion, common sense. So let's say we have 4 equals 3 plus 1, right? Those are equal. 4 equals 3 plus 1. If I add 2 to the 4, then I have to also add 2 to 3 plus 1. That's what that's saying. If equals are added to equals, then the wholes are equal. So we're adding 2 and 4, and we're adding 3 and 1 and 2. We're getting things that are added together. Here's the next one, then they're both balanced. If equals are subtracted from equals, then the remainders are equal. All right, I see you. So if equals are subtracted from equals, so let's go back to this. We have 6 equals 5 plus 1. Now, if I put a gap right here for a reason. Because if I go 6 minus 3, the answer is 3. 6 and 5 plus 1 are the same. So if I take away 3 from the 6, I have to also subtract 3 from the other. That's a common notion. Things that coincide with one another equal. What does it mean to coincide? It means things line up, things stack. And so when we've been doing stuff with tracing paper, which I don't have any next to me right at the moment, but when we're doing stuff with tracing paper, if we've got like a shape and I have another shape and I can make that shape land on this one, like trace it and move it through translations, that makes them coincide, well then they must be the same. Or if I draw a triangle like this and I draw another triangle like that, this line that is shared, this line segment shared by both of them, must be the same length because both triangles have a side that line up, that coincide. Math word. Okay, his fifth notion, which these are common sense. So if these are not common sense to you, let's talk about it. The whole is greater than the part. So like 1/2 versus 100%. One of those is bigger. Like 1/2 is the part and 100% is all of it. The whole, as they say. Those are Euclid's 5 notions. All right, I want to set another video here for you. So I'm going to go ahead and acknowledge that we are going to do the linear pair postulate in the next video, the segment addition postulate in the video after that, and the angle addition postulate in the fourth video of this sequence. Thanks for watching all 12 minutes. Oh my gosh, you're amazing. Maybe you clicked through really quickly. Appreciate it. Awesome. I'll see you in the next video. And yeah, ask me any questions when you get the chance. Thanks. Bye.